In the previous video, I introduced you to the most important formula that we've seen so far in this class. This difference quotient formula, which allows us to figure out the derivative of a function at a given point. We use this formula to figure out the slope of the tangent line to this curve, f of x equals x squared minus 3x, at this point where x is equal to 2. But the beauty of this formula is it works for any function at any point. And in case you don't believe me, what I'm going to do in this video is demonstrate it with a bunch of different looking functions. First, suppose the function we're interested in is x cubed minus 2, and we want to find f prime of 3. The first thing you want to be able to do is understand what this is asking. This is asking you for the slope of the tangent line to this function f of x, which in this case is defined to be x cubed minus 2, at the point where x equals 3. That's what this means. And the way you figure that out, you say f prime of 3 is equal to the limit as h approaches 0 of f of 3 plus h minus f of 3 divided by, if you want, you could write 3 plus h minus 3 on the bottom, but 3 plus h minus 3 is just equal to h, so most people cut straight to this step. This is the slope of the secant line, the change in the y values, divided by the change in the x values. Again, 3 plus h minus 3. And by putting the limit out in front, we're changing the secant line into a tangent line. From here, all that's left to do, maybe in big air quotes, is the algebra. Really, this is a problem for the previous section on limits at this point. To figure out f of 3 plus h, just copy this formula, changing all the x's into 3 plus h's. So I get 3 plus h cubed minus 2. And from that, I want to subtract f of 3. To figure out f of 3, just copy what you see up here, changing all the x's into 3's. 3 cubed is equal to 27. 27 minus 2 is 25. And then I divide that expression by h and take that limit. If you think about what we're doing, eventually I want to change all the h's into zeros, but if I try doing that right now, I would get 3 cubed, in other words 27, minus 2 minus 25, the top would be 0. And if I change all the h's into zeros, the bottom would be 0 also. So 0 is a root of the polynomial up top and the polynomial on the bottom. Therefore, h minus 0, in other words h, is a factor of the polynomial on the top and the polynomial on the bottom. This h is the one that's causing trouble. This is the one that's got to go. There's got to be an h up on the top that I can cancel this h with. It's tempting to try to cross these out or something, but that algebra doesn't work. What we instead have to do is expand this binomial. Just so my work doesn't get too ugly, I might do that off to the side. I need to know what 3 plus h cubed is. One way you can think about this is it's 3 plus h times 3 plus h times 3 plus h. I'm multiplying together these three things. I can multiply together the first two pretty easily. 3 times 3 gives me 9. 3 times h gives me 3h, but h times 3 gives me another 3h, so I got 6h, and h times h gives me h squared. That's not my answer, that's just the product of the first two things. I have to take that and multiply it by 3 plus h. When you're multiplying a trinomial by a binomial, it's a little bit tricky, but it's kind of the same logic as what we did when we multiplied these two binomials, 3 plus h times 3 plus h. You just have to make sure that each of these terms, the 3 and the h, gets multiplied by each of these three terms, the 9, the 6h, and the h squared. So maybe I'll first take the 3 and multiply by each of these terms. 3 times 9 gives me 27. 3 times 6h gives me 18h. And 3 times h squared gives me 3h squared. The 3 has been multiplied by each of these terms. Now I got to make sure the h gets multiplied by each of these terms. The h times the 9 gives me 9h. Maybe I'll write that down here. The h times the 6h gives me 6h squared. And the h times the h squared gives me h cubed. Adding up these 6 terms is pretty easy because of the way that I wrote it. I got 27 plus 18h plus 9 more h, so 27h, plus 3h squared plus 6 more h squared, so 9h squared, plus this h cubed. Wait, what were we doing? 3 plus h cubed is the same as 27 plus 27h plus 9h squared plus h cubed. So in place of writing this 3 plus h cubed, I could write 27 plus 27h plus 9h squared plus h cubed. But that's not the entire top, that's just this 3 plus h cubed. I got to make sure that I don't forget that I got a minus 2 and a minus 25 here. In other words, minus 27. The denominator is still just this h. I've gotten rid of all the parentheses here. Hopefully that'll help me simplify stuff. Let's see what happened. I got this 27 and this negative 27. It looks like my constant terms canceled out. How nice. Now what I'm left with up in the numerator, 27h plus 9h squared plus h cubed, is a bunch of terms that each have an h in them. So I could factor out that h if I wanted, and that h that I factored out could cancel with this h, and what I'd be left with is 27 plus 9h plus h squared. This expression is not the same as this expression, but they're very similar, which is why their limits are the exact same. The good thing about this expression is it's continuous when h equals 0, whereas this expression has a removable discontinuity when h equals 0. So evaluating this limit is a lot easier. Just change all your h's into zeros. 27 plus 0 sounds like 27. F prime of 3 is equal to 27. If I were to sketch this graph and I were interested in the slope of the tangent line when x was equal to 3, I would find that that line is a really steep line. It's got a slope of 27. Let's see if we can fire through a couple more examples. What if instead of f of x being x cubed minus 2, f of x was 10 minus x square rooted? Really, it doesn't matter. Now I want to find f prime of 1. Fine, I'm going to use the exact same difference quotient formula. It's the limit as h approaches 0 of f of 1 plus h this time minus f of 1 divided by h. You can memorize this if you want, but it'd be awesome if you can kind of see what's going on here. y2 minus y1. And then this is what you get when you take x2 minus x1. Anyways, don't forget to write your limit. We got the limit as h approaches 0. F of 1 plus h is pretty easy to evaluate. I just copy this blueprint up here, changing all the x's into 1 plus h's. So I got 10 minus 1 plus h. From that, I want to subtract f of 1. F of 1 would just be the square root of 10 minus 1. In other words, the square root of 9. In other words, 3. And I want to divide that entire thing by h. Oh, this is really ugly looking. What am I going to do? Well, what I'd probably do is clean it up a little bit first. If I take this negative and distribute it through the parentheses, I got 10 minus 1 minus h. In other words, 9 minus h underneath this radical. And the square root of 9 is just 3, so maybe I'll just write this as minus 3 and divide that by h. You don't really have to do this step, but cleaning it up makes it a little bit easier. You'd love to evaluate the limit the way it's written right now, but bad news, you can't. Why not? Because try it. Try changing all your h's into zeros. You'll get 0 over 0. Why? Because this has a removable discontinuity when h equals 0. That's always going to happen when we evaluate these difference quotients. That's why we spent so much time on that specific case in the previous section when we're talking about limits. Oh, right, okay, and I think you even showed me an example where we evaluated a limit with a square root sign in it. Yup, there was a trick to that. You remember what the trick was? If you do, you might want to pause the video here and see if you can finish the problem from here on your own. The trick was we're going to multiply the top and the bottom by the conjugate of the top. The conjugate of the square root of 9 minus h minus 3 is almost the exact same. We write the square root of 9 minus h, the first term, and then we write 3, the second term, and all we do is change the sign in between those two terms. So this minus changes to a positive. If I'm going to multiply the top by the square root of 9 minus h plus 3, I better also multiply the bottom by the square root of 9 minus h plus 3. It looks like we've made this limit way more complicated, but what you'll see when you multiply something by its conjugate, things work out really nicely. The square root of 9 minus h times the square root of 9 minus h is just 9 minus h. Think the square root is being squared. The square root of 9 minus h times 3 is the exact same as the square root of 9 minus h times negative 3, except one of them is positive and one of them is negative. So when I add them together, those cancel out. I don't even need to write it. Negative 3 times positive 3 gives me a negative 9. My numerator is cleaning up really nicely. In the denominator, you could take the h and distribute it through the parentheses, but I wouldn't recommend doing that because remember, our goal is to get rid of this h. So I'll leave the h factored out and just write the square root of 9 minus h plus 3. Up top, the 9's cancel out. I probably don't need a separate step to do this, but we've gone this far. Here's cleaning up the top. Maybe now you can see that these h's cancel out. When I cancel out these h's, what I'm left with is the limit as h approaches 0 of, up top I just have a negative 1, and down in the bottom I got the square root of 9 minus h plus 3. This limit is a lot better than this limit. Even though the limits are equal, these expressions are not equal because this expression is undefined when h equals 0, but this expression is not undefined when h equals 0 because this expression is continuous at h equals 0. Its limit is super easy to evaluate. Just change all the h's into zeros. I get negative 1 divided by the square root of 9 minus 0, in other words 9, plus 3. Square root of 9 is just 3. 3 plus 3 is 6. It looks like my answer is negative 1/6. The slope of the tangent line to this curve when x is equal to 1 is equal to negative 1/6. One more example, then we'll call this video good. So far, we've looked for the tangent line to a polynomial and the tangent line to a radical function. What we haven't seen is the tangent line to a rational function. And based on the examples we've done in previous sections, maybe those would be the three types of functions that you'd expect. When our function is a polynomial, the limit that we have to evaluate is just a quotient of polynomials, so we just have to get rid of the parentheses and factor out an h from the top. When the function is a radical function, the limit that we have to evaluate has these square roots in it, so we have to employ that trick that we learned where we multiply by the conjugate to get rid of that square root. When the function we're interested in is a rational function, what you'll see is that we end up with fractions inside fractions. But that's okay. In the previous section, we learned how to deal with that. Without further ado, let's figure out f prime of 2. F prime of 2 is the limit as h approaches 0. Think the 2 points are getting infinitely close together of the slope of the secant line. What's the slope of the secant line? It's the difference in the y coordinates, f of 2 plus h minus f of 2, divided by the difference in the x coordinates, 2 plus h minus 2. In other words, h. Since f of x is 5 over 2x, we can rewrite this expression without the f's in here. F of 2 plus h is exactly what you see here, except we change all the x's into 2 plus h's. So we would get 5 divided by 2 times 2 plus h. From that, we want to subtract f of 2. F of 2 is exactly what you see here, except change all the x's into 2's. So it's 5 divided by 2 times 2. In other words, 5/4. Want to divide that entire mess by h. This is the limit we need to evaluate. How do you evaluate a limit like this? Well, you got these fractions inside fractions, right? You've seen that before. The way you get rid of fractions inside fractions is you make it one fraction divided by one fraction, and then you take the one on the bottom, flip it upside down to change the division into multiplication. That's exactly what we're going to do here. The first challenge, probably the biggest challenge, is if you look up in the numerator here, you see two different fractions, not one fraction. You wish that was two different fractions, but it's not. It's just one. So what we have to do is subtract these two fractions to make them a single fraction. Problem with subtracting fractions is you can't do it unless you got a common denominator. Fortunately, I can make these guys have a common denominator. Probably the easiest way to do that is multiply this side by 2 over 2. That makes this denominator 4 times 2 plus h. And then multiply this side by 2 plus h over 2 plus h, which makes this denominator 4 times 2 plus h. What I have is 2 times 5, in other words 10, divided by this common denominator of 4 times 2 plus h, minus 5 times 2 plus h, which I guess I could write as 10 plus 5h, divided by this common denominator of 4 times 2 plus h. That entire thing is divided by this h. This is the expression I need to simplify. Couple comments here. Because of where I put the minus sign, there's implied parentheses around the top here. And that's really important. If it helps you, you can write the parentheses there, because we got to make sure we subtract all of this stuff. It's tempting for students to look at this and think the 10 is negative, but the 5h is positive, but it's not. I could either take the positive 5 and distribute it through the parentheses, but then I got to make sure I subtract the entire thing, or I could have taken the negative 5 and distributed through the parentheses to make this negative 10 minus 5h, which would have made this a plus, this a minus, and this a minus. Either way is fine. Just make sure you're doing one or the other. Can we clean this thing up a little bit? Yeah, absolutely. Now that we have a common denominator up in the numerator here, I can subtract these two fractions. When you subtract fractions with the common denominator, you just write that denominator a single time, 4 times 2 plus h, and then you subtract the numbers up in the numerator. So I got 10 minus 10 plus 5h. 10 minus 10 cancels out, and I'm left with just negative 5h. In case you can't follow that, what's going on is it's 10 minus 10 plus 5h, which when I take the negative and distribute it through, makes 10 minus 10 minus 5h. These cancel out, and I'm left with negative 5h. Be really easy to leave this as a positive, so be careful here. That's the top. Down on the bottom, I got this h, which maybe I'll write as h over 1, so it looks like a fraction over a fraction. I'm now at the stage where I can change this big division here into multiplication. The way I change division into multiplication is I multiply by the reciprocal of the denominator. I got the limit as h approaches 0 of negative 5h divided by 4 times 2 plus h. And then instead of divided by h over 1, it's times 1 over h. Great thing about this expression is this h and this h can cancel out, because up top I just got negative 5h times 1, in other words negative 5 times h. And in the bottom, I got 4 times 2 plus h times h, a bunch of stuff being multiplied together. You can cancel over multiplication. I got negative 5 divided by 4 times 2 plus h that I'm trying to take the limit as h approaches 0 of. This limit is a lot easier to evaluate than this limit because this limit is discontinuous at 0, but this limit is continuous at 0. So evaluating the limit is super easy. Just change all the h's into zeros. If I change all the h's into zeros, I get negative 5 divided by 4 times 2 plus 0. In other words, 4 times 2. I get negative 5 divided by 8 as my answer. The slope of the tangent line to this function, f of x equals 5 over 2x, when x is equal to 2, is negative 5/8. I tried to go really quickly through those examples because really they were review, as weird as that sounds. You could argue that the only new thing we're learning in this section is learning how to set up these problems. If you can get to this stage right here, or this stage right here, or this stage right here, these problems become a problem from the limit section. I purposely chose examples in the limit sections to set you up for these problems so that when you learn this really complicated theoretical idea about the derivative, the algebra is already kind of done for you. You're just repeating things that you learned in the previous section. That was my hope anyways. Hope that went okay for you.